So, okay, hi everybody. Thank you for coming. It's great. Just to make sure you can ask questions in the Slack channel in track 4, or you can do it in the WebEx chat. I'll be happy to answer those probably towards the end of the talk, so I don't get interrupted too much. So hi, my name is David. I'm the chief architect of Proofpoint's information protection systems. We make cloud security software, and not trying to sell you our systems is going to be very relevant to this talk, because pretty much everything I'm going to talk about in regards to distributed asynchronous microservices, it's stuff that we're either doing or implementing or trying to do at work. And usually my talks are very grounded in stuff that I'm doing in real life. It's not theoretical at all. It's usually based in practical things that we've done. So today we're going to be talking about asynchronous versus synchronous models of microservice systems. And why you would use one over the other, what they actually mean, what the trade-offs are, how to think about concurrency and asynchronicity in distributed microservice systems. I'm going to keep saying the word microservices until it, or distributed, so much is going to lose meaning at some point for everybody. It's just going to be noise. So yeah, let's dive into it. Generally speaking, let's talk about what the difference really is between synchronous and asynchronous systems. It's not that one is better than the other. I want to make it clear, both of them are very legitimate design patterns, and there are good reasons to use one or the other, or a mix of both. Oftentimes, when you build a brand new system and you don't know exactly how it's going to evolve, it makes a lot of sense to use synchronous protocols to communicate between services. HTTP is, of course, by far the most common. That's basically the de facto standard if you want to have microservices and you talk to each other. It's usually going to be some form of HTTP. If you need better performance and less overhead, probably you'll do some kind of gRPC version, or there are a few other synchronous ways for microservices to communicate. And obviously, the benefit of that is it's very straightforward. There are excellent tools. The observability, which means figuring out when exceptions happen or figuring out if something went wrong, is much easier because the exception happens as part of the call. You can find all of the logs for exceptions in the same small space of time in the logs, and you can handle errors synchronously in line. For example, if you have a web client, it will get the exception immediately to any operations, and you can show an exception to an error to the user and stuff like that. And the failure modes are well understood because we've had synchronous systems for a very long time now. The bigger problem with that kind of system is it introduces a lot of temporal coupling between different components. And what I mean by that is if a particular dependency of our microservice system is currently not available, for example, a database is down or a service is a process fell and the load balancer still hasn't switched over to a different one, then that failure propagates through the entire system, right? So if you have a set of microservices, each call on each other. Yeah. If you guys could mute, that would be very good. So if you have a couple of microservices calling each other, the lowest dependency will, if it goes down, it will actually take down the entire chain of services with it. On the other hand, when we talk about asynchronous systems, usually there's some kind of queue or buffer involved between the different systems. So services don't talk to each other directly. They talk to some kind of message transport or queue, and the component on the other side of that transport will read the message whenever it feels like, maybe very quickly, maybe an hour from now. And so a lot of the time, those would be data write-oriented systems where you have to perform a lot of writes or updates. And those systems break up the temporal coupling, which means a service could be down, but not affect any of the upstream or downstream dependencies, because all of those dependencies can continue working, and eventually one service will recover and process whatever queue messages were queued up. The bigger issue it introduces usually is high complexity. Because there is no temporal coupling, any errors get actually spread out over time, right? So if a service went down, and it went down because something that a different service did that is 3 hops away from it in the microservice system, you might find log messages and spread out apart an hour or more, both of which let you actually debug this error. But the uptime or the upside of actually using asynchronous systems is usually they're more resilient, they're easier to scale because they're decoupled better than synchronous systems. So that's broadly what we're going to talk about, and throughout this talk, we'll actually dig into the reasons to choose one over the other, and some useful patterns for asynchronous systems, and how to think about the reasons for switching, right? And so why would you actually go from one to the other? The biggest one is, like I said, the temporal coupling. As a system grows, I'm not talking about 1 or 2 microservices, it's not really meaningful there. But for example, the system I mostly work on, which is Proofpoint's cloud security product, we're at over 100 microservices right now, and it keeps growing because we have a large team of people working on this. It's a very complex system, and breaking apart the temporal coupling between different services, which means if one service goes down, it takes out a bunch of other services that depend on it. That was a very large part of why we completely switched from synchronous modes of communication to asynchronous ones. And of course, scale, which is really a consequence of that, is another. The different failure modes, and we'll talk about this at length, is going from synchronous to asynchronous basically replaces lack of availability or a system being down with latency. So an operation will eventually happen, but it's going to take time for the fault to resolve itself. And of course, there are different ways of doing CRUD, and a lot of the reactive patterns in programming we have today, RxJS, a bunch of other reactive frameworks, they're all very strongly oriented towards asynchronous message buffering systems, right? But the biggest reason, of course, is breaking up the temporal coupling and resolving different failure modes. And to understand really the core trade-off between synchronous and async systems is, let's look at this diagram. Let's imagine we have 2 services. We have a client service, we have a server service, so to speak, and it has some kind of database or data store attached to each one of them. And let's imagine the scenario where the database goes out. So what happens in the synchronous service versus what happens in the asynchronous one? In the synchronous service, of course, the service that depends on the database synchronously, meaning it writes the database directly or reads from the database directly, is of course also down, right? Because its own purpose to exist is to do stuff with the database. It's a sort of a CRUD service. And so if the database is unavailable, that means the backend service is also unavailable. With the asynchronous model, that's not the case, because the asynchronous service buffers the writes in some magical place, which we're not going to talk about right now, but we will get to in a bit. But for now, work with me. Let's imagine there's some magic that happens, and the asynchronous backend service puts its data somewhere, and then eventually it gets to the database. And we'll talk about this somewhere at length, right? But just because the database went out doesn't mean the service is down. You can still talk to the service, and it can still fulfill its function. So right there, we're trading some of the consistency of the service, which means it doesn't write data to the database immediately. It will write it there eventually, but we're trading it for availability, which means the service continues being up and functioning. And of course, in the async mode, the client service is always up because, again, it also talks to the backend service asynchronously. And so the fact that a database 2 hops away went down doesn't affect its availability. So this would give a much better user experience, for example, if this was a UI application or any kind of service. With the synchronous mode, we're not actually sure what the status of the client service would be. It might get an exception from the backend service. It might also be down if it's a GUI application, depends how you write it. It might hang or throw an exception. So basically, a downstream dependency going down will strongly affect the entire call chain of the synchronous mode, whereas with asynchronous, obviously, you maintain functionality. Unfortunately, what that means is, of course, what you're doing is you're introducing latency instead of an exception, right? So we're trading one failure mode, which is unavailability, for a different failure mode, which is latency. And this is going to be at the core of the reason of why we choose synchronous over asynchronous or the other way around, what failure modes we actually prefer. And for different applications, different failure modes make sense, right? So for GUI applications where if you want to make the error apparent to the user immediately, you might choose something that is actually synchronous and then let the user handle the exception. For standalone applications, as an example, our system, the Proofpoint CASB, most of the data comes into the system from automated systems, from some scheduled jobs which go to cloud providers and bring in information about user activity. And all that stuff is standalone. So there's no person to click OK on an error message. So all of that, in this case, we strongly prefer to incur latency and just handle the workload later over the system just being unavailable and missing a lot of data because it will not be repeated, right? And so that there gives you the reasoning of why you would choose one over the other. In a client application, we will likely, especially for the read path, which we'll talk about a bit later, you will probably pick a synchronous mode of operation so that you can actually present the error to the user quickly and let them handle it. In a standalone application or something that receives data that can't be repeated, you will likely choose async modes because they let you persist data and handle it after that failure resolves, right? And so this core trade-off really brings us to one of the bigger topics usually in distributed databases. Anyone who's actually done any kind of work with NoSQL databases and distributed systems almost certainly run across the CAP theorem. The CAP theorem, which was proposed by Eric Brewer, a computer scientist from Berkeley, and then proven formally as a theorem a few years later. What it says is, specifically it talks about distributed databases, but if we think about microservices as front ends for different data stores or just of themselves, it can also somewhat apply to microservices, and I'll explain how in just a bit. But basically, the CAP theorem says for any distributed database or distributed system, it can provide at most 2 out of the 3 guarantees, like as follows. Consistency, so every read from the system receives the most recent version of the data or an error. So if you can imagine, if it's a service that fronts a database, you write something to the database, you read it back immediately, and you get the version you wrote. Availability, which in this case means that every request to the system receives a valid non-error response, right? It doesn't have to be current, it doesn't have to be updated, but it has to get in a response that's not a timeout or an error. That's the definition of availability for CAP theorem. And partition tolerance, which means that the system can continue to function despite losing an arbitrary number of messages or delaying messages between network nodes. Now, if you think about modern systems, the real trade-off here is always between consistency and availability, because a system which doesn't have partition tolerance, a distributed system without partition tolerance, is not really a practical production system, right? If it has an undefined behavior because it loses network packets or messages, that system is not robust and you're not going to really put it in production. And so for practical purposes in real life, we get to pick between a system that's either partition tolerant and strongly consistent or some kind of consistent, or it's partition tolerant and highly available, but not both at the same time. Now, notice that the word at the same time here is very important. A system can be one or the other at different times and flip between those two according to exceptions or configuration. But at any given moment, that's the way it works. So to demonstrate it, I usually do this in person. So it's usually a quiz and people can raise their hands and stuff. So we'll see if this works virtually. So think about a bank machine, an ATM or whatever it's called in English. You go to a bank, there's a teller bank machine at the wall, you want to withdraw some money. And there's 3 different machines, right? And just as you go to withdraw money, what happens is the bank loses network connection to the main computer, the mainframe. So now this ATM doesn't have a network connection and you try to withdraw money, what's going to happen, right? So one of 2 things is going to happen. Either it will let you withdraw some money, but then it won't be able to update the backend system until connection resumes, or it will not let you withdraw any money, which means either it's an available system and then you can continue using it and you get a valid response. In this case, the response is money, or it's a consistent system. You go to it and you receive, and you don't get the latest result. You can't update the system, but it doesn't actually create an inconsistency between the bank machine and your actual bank account. So who thinks banks would put up a consistent system for ATM machines? Raise your hands. I can see you, but you can raise your hands. See, 1 person thinks. Excellent. Thank you very much. So who thinks it's actually going to be an available system, which means they will prefer user experience to let you continue using the bank and withdrawing money over consistency? Anybody? Okay, so I can't see how many people. 1 person. I saw 1 person vote, but I can't see the rest of you. So I'll just tell you the answer. For most banks, and again, it varies by different countries, and there are some regulations which affect it. But for most banks, they will actually prefer to let you withdraw money. So an ATM which lost network connectivity will still dispense money up to a certain limit. The limit obviously depends on what kind of account you have and what bank and stuff, but it will let you keep withdrawing money. Of course, it doesn't really happen very often in real life. How often does a bank lose network connection? But a long time ago, it used to happen quite a bit. And there were actually very famous attacks on banks where a person was able to disrupt the network connection and withdraw money from a bunch of machines in a row. But normally what will happen is you can withdraw money if it means that your bank account will go negative. That's actually not a bad thing. Most banks will let you go into a negative balance because they can then charge you interest on the negative balance, and it's to the bank's advantage. And so they prefer user experience over consistency. But that's just to demonstrate the trade-offs you make in consistency versus availability. And if you were to now design a bank machine system with microservices, you would have to think of what do you do in every failure scenario in this case, right? So that's broadly speaking the CAP theorem, and the way it applies to microservices, of course, is again, we have to split up the read path and the write path. So when you write to a system, if you want the read, which means you have a UI application, and it's very important for it to be consistent, you might choose a synchronous system, which will go and update a database. And then if you refresh the page or somebody else uses this information, it will be available immediately. It will be consistent with whatever you wrote. Versus an available system where you will possibly queue up or buffer writes to the system. And so if you can't write at that moment, they will eventually get written. But that means that the user or whoever reads the data will get an inconsistent, a stale view of the system. Right? And that's our trade-off, right? And so I keep saying queue up or write to this magical place without explaining what the magical place is. So it's time to talk about where would you actually put it. It's obviously not a secret, and I'm sure everyone thought of it. We're all familiar with queues and various message transports. But overall, and I'm not going to talk about a specific vendor or specific technology. And they're broadly, we'll talk about use cases and broad categories of queues, but not a specific technology. But broadly, asynchronous system designs assume that the message transport they use to send messages between services is reliable and robust. This is like the dirty little secret. Asynchronous systems aren't inherently more highly available. It's just you move the availability or the failure point to one central system, which is your message transport. And then you put a lot of effort into making that as robust and available as possible, instead of making each individual service or each individual component as robust as possible. Overall, if your message transport goes down, the entire system is still going to go down, right? Unless you build some kind of hybrid, very complex system, which is not something I've ever seen in practice in real life. But yeah, you have to assume that the message transport is reliable, which means talking to it is consistent or at least durable, unless, of course, data loss is acceptable. And that's not a joke. There are systems where data loss is actually perfectly acceptable. Systems that look at, for example, the latest snapshot, the latest state of data or statistics. For example, think about the trivial example is a stock ticker, right? I don't care usually to show the history of all the stocks. I want to see the latest price. And if I missed 5 or 6 updates, I'll just show the next update and it's fine, right? So there's going to be a slight delay. And so in that case, an asynchronous lossy system is okay. But for most practical applications, when you're thinking about real world production systems, data loss is not really acceptable. And so we kind of have to assume that message transports are. And this is actually true for most of them, because almost every messaging technology that's in use and popular today has built-in redundancy and replication and a lot of features around guaranteeing durability and reliable delivery of data. A lot of them are SaaS systems, right? So if you're on kind of public cloud, every single public cloud has their own offering or multiple offerings, really. Amazon has Kinesis and SQS and SNS, and Azure has Event Hubs, and Google has a thing which I can't remember the name of. But everyone offers one of those, and all the big vendors have their own cloud offerings. So if you're building a new system, you don't even really need to put in that much effort into making it available. You can just buy that from someone, obviously, by paying lots of money. Let's assume that our transport is in fact available and robust, and let's talk about what we can do with it, right? So now that we've sort of established that in the case where we want our system to be asynchronous, or some part of our system to be asynchronous, and we will later on talk about how to make a hybrid synchronous versus asynchronous system and where it makes sense, there are some patterns which help us. Just like there are design patterns in coding, which cover a lot of common use cases, in asynchronous messaging patterns, there are standard design patterns which you can apply to your system. We'll go through them real quick. The easiest and most common is fire and forget, is where you post a message to some queue. You don't expect a response, and you do, if you want the transport to be reliable, you do expect an acknowledgement from the transport itself, but not from whoever receives the message on the other side. So in a trivial example, so at Proofpoint, we use Kafka for most things. So a Kafka producer, what it does is it writes a message to a topic, and then it commits the, it waits for the topic or for the broker to respond and say that, yeah, its message has been durably committed, and only then it moves on. You don't just move on and assume the message has been passed. But it doesn't wait for an acknowledgement from whoever consumes the message on the other side of the queue, because that's not fire and forget. That's the next pattern we'll talk about. So that's actually very useful. Most of this is very used in data processing pipelines. So again, the product I worked on a lot, the Proofpoint Casby, is basically just a giant pipe which moves data from one side to the other and does various transformations with it along the way. And it's built just as a series of these kind of drawings. We have a service which gets data, does something with it, puts it in a queue. We have on the other side of the queue a different service which gets the data, does something, puts it in a different queue. And it doesn't expect a response back and it doesn't send anything back. Data just moves downstream from one to the other until it reaches some endpoint, usually a database, right? And so this is by far the most common, most useful pattern in asynchronous communications we have. It's also very robust because, again, there are very few dependencies. Every service only depends on the message transport itself. It doesn't depend on anybody else or any other response. And there's actually very little coupling between components. The biggest downside, of course, like with most asynchronous system here, is debugging it. Because if you expect service A to send something to B and C and D and however many letters next, if the message doesn't get to the end, figuring out where it went away or which service lost it is very much non-trivial, especially if there's latency in the system. We'll talk about this towards the end of the talk and expand on it. But if there's latency in the system, there might be two error messages produced by two different services, and they're not actually in the same time frame. There might be a lag of an hour between two services, and so while we'll log an exception an hour later from the other, and how you find those and correlate those is a very complex problem, which we will answer in this talk. So the next pattern is publish a subscriber. It's just an upgrade of the previous notification pattern, where fire and forget is between two components. PubSub, publish a subscriber, is again a very well understood pattern. Everyone, I'm sure, used it at some point in their lives, either between threads within a single process or maybe between processes, is where one or more components publishes a message and then multiple components subscribe to receive those kinds of messages. Right. And again, there's no expectation of a return message. It's still kind of a fire and forget pattern. The biggest difference here is, of course, that you can configure whether all the subscribers receive the same message or a single subscriber receives a copy of the message. There are lots of variations. They're all very useful in their way. And the biggest difference here, of course, is whether the transport is durable or transient. So transient patterns would be something like the default mode of RabbitMQ and a few others, notification systems, where you send a message and anyone who was listening to that message at that moment in time will get the message, and anyone who missed it will miss the message. And that's fine for, as an example, the previous example we had with the stock ticker. We send the update. Anyone who got it, excellent. Anyone who missed it, it's fine. It's no big deal. For more robust production systems, of course, you want durability in the transport. You want a subscriber who went offline and came back to be able to catch up and get all the messages it missed while it wasn't listening. And so you would have some kind of durable transport instead of just a message broker that just sends the messages forward. Right? But either way, it's a very useful, very common pattern. We use it again a lot because it's just a logical extension of the notification pattern. If we have some kind of message, let's say a user performed an action, and we have three different services which are interested in that kind of message. One service goes and updates the user profile. Another service goes and runs heuristics to analyze the activity, and the third service goes and does something else. They all care about this message. They're independent of each other. So in this diagram, C, D, and E don't rely on each other. Each service will do an independent thing with the message it receives. And so it makes perfect sense to decouple them temporarily because we don't want the state of one service to affect the availability of all the others. So this is where we would use this kind of pattern. Makes a lot of sense. The next one, and this pattern is what most closely mimics known synchronous patterns, which is request response. It's the best analog we have to, for example, asynchronous to a space synchronous HTTP request, where you make a request and you wait for a response and you expect something back. Of course, in an asynchronous system, that can take an arbitrarily long amount of time. But the pattern is service A sends something to service B. Service B does something with this message and then returns a different message to service A. The biggest difference between the synchronous version of this pattern and the asynchronous version is in the synchronous version, usually the service which originates the request maintains the context of the request in memory, in the thread. For example, if you think about the standard HTTP service, it calls another microservice, gets a response back. You still have the object which you used to create the response in memory. So you can handle the response in the same thread. You don't need to store the context somewhere else. When it's asynchronous, we have multiple instances of service A. We have multiple instances of service B. Let's say A1 posts a message. Service B1 receives it, posts a message back, but then nothing guarantees that service A1, that instance, will receive the return message. A different service will pick it up, maybe A3. And A3 doesn't share memory with A1. They're different instances, they're different processes. And so you have to handle this propagation of context. If the return message only makes sense, if the response makes sense only in the context of the request, how do you propagate the request back to the service A, which received the response? Right. So there are multiple ways, but basically they boil down to where do you store the state? You either put it in some kind of database or somewhere, which has its own trade-offs because now you're introducing a synchronous A space synchronous dependency for service A, because A has to first store the message with the context in a database, send the request, get the response, get the context synchronously from the database and merge those two. And so you're kind of breaking away from the asynchronous pattern. Or the more common, but slightly more expensive version is you send the entire request with the context and everything as part of the message, and then service B has to return its response and the request or the request context together with the response. And so in this case, the response travels back and forth. You're sending more data. Sometimes it's practical. Sometimes if it's too much context, it's just impractical to do. It's too expensive. It's too large. It doesn't fit. But that way you avoid any kind of synchronous dependencies. Right, and so in our system, it's about half and half between those two use cases. We do have cases where we get a large message. Just an example, one of the features we have is data leak prevention. So we download the file, and then we need to scan this file and classify the data. Is it PII, private data, or classified data, stuff like that. So we download the message, but the message is large. It could be 20 megabytes of file. We're not going to send the entire file over, in our case, Kafka. It's just not practical. So what we'll do is we'll store the file in some kind of shared file system. We'll send a message with a pointer to the file to a different service, which will use the file, do some stuff, put the response, the blob of response somewhere else, send the message back saying the response is ready, and here's a pointer to the response. Right? And so this mixes synchronous and asynchronous modes. There are obvious downsides to it, but it's just a practical reality that we couldn't make it work completely asynchronously. We had to compromise and make it half and half. In many other cases, we send the request and persist the context on the request, and that's obviously preferable if it's practical to do so. Right. So then the next expansion of the same concept, of course, is the distributed log, which is just another way of saying pub sub, but you don't have to sub, which means subscribe, to the tail of the queue. Right. This is the way a lot of the popular services work. Kinesis, Kafka, Pulsar, most of the message logs that have memory let you actually consume messages not from the top of the queue, but from any point in the queue. And they have a history, potentially going back days or years, however long you want, of all the data that's ever been logged in this message log. And that's why we call them different things. So it's not a message queue, it's usually a distributed log because you have a log of all the messages. And a lot of the time, you also have some kind of compaction feature which will duplicate similar messages. Right? And so this pattern is extremely useful for data processing applications or for just being able to reprocess data very quickly. One very strong use case for this is we have a service which maintains user profiles. What it does is it gets information about users from directory services, things like title, name, blah, blah, blah. And then it tries to figure out if that user is an executive or not, according to their business user and the title. There's a lot of natural language processing on the title and the business unit, and tries to figure out if that person is an executive or not. For us, the reason is an executive is more vulnerable to security attacks, and we have a security system. So we try to figure out and classify if that person is more vulnerable or not. And so this algorithm has gone for maybe 50 different versions. And so we have a data store of maybe hundreds of millions of users we know about. And so every time we roll out a new version of this algorithm, what we want to do is obviously put it in production so that any new updates to the users come in through the new version of the algorithm. But we also want to go back and reprocess all of the old messages and update them, because now we can calculate whether they're an executive better than before. But we don't want to have downtime in the system. We're not going to just stop everything, put up the new version in production and let it run and then accumulate new messages. What we normally do is we spin up a second version side by side with the old service, and we point the updated version to the end of the queue of user updates and let it start consuming. And it usually takes a day or two. It goes through the entire log of all the users we've ever seen, and it keeps updating the database. At the same time, the old version still works and is still running the old version of the algorithm on the real-time data. Eventually, the new version catches up to the log, and then we bring down the old service, and only the new service remains in production. And so we do the switch over between two different algorithm versions in real time without losing functionality. And it's completely seamless. Right? So that's a very strong use case. If you can map it to any kind of stream processing you have, it's probably going to find some use there. And it works basically the same way, right? You have one or more publishers and however many subscribers. And the benefit, of course, is that any subscriber, a new subscriber, can join and find all the messages that ever existed if it wants to. And we'll talk about this in just a moment a bit more when you talk about event sourcing. Now they have all these basic communication patterns, right? We can start combining those into more higher level patterns. And the biggest one, and I think probably by far the most useful when you build an asynchronous system, is CQRS, which is command query responsibility segregation or separation, which it's a very large topic. It could be a talk in and of itself, but to summarize it into 3 minutes, very often in traditional architectures, we use the same data model to both update a database and to query from the database. If you think about it as an example, let's say we have some kind of user object. We have a table of users. A user update comes in. We write the user. We want to show that. If you want to show it in the UI, we do select on table star from table users. Hopefully nobody does select star. Please use the full attributes. Select star is a bad practice, but roll with me. And so we use the same model to actually both update and get the data from the database. Now, at large scale or at a complex enough system, when you have a large enough data model, that doesn't work very well, because oftentimes the model we want to read is not the same as the model we want to write to the database. For example, again, our example, we have the user store system, which aggregates user profile information from hundreds of different directory services. A user object, in our case, has many sub-objects. It has a bunch of information about various accounts. It has history information about what we saw about the user. It has all of the profile information. So there's a bunch of different subcategories. Each one of those gets updated separately. If we were to model this in a normalized way, it would be maybe 50 different tables that we have to all join together. But when we want to read this user, we don't care about all of that multiple model stuff. We want just one giant user object, because we want to optimize the system for low latency, high throughput reads. In our case, the third generation of our user management system has at peak about 1 million requests per second to it, right? But pretty much every other subsystem in our product calls to the user system to do something with it, and it's a crucial piece of the infrastructure. And so it needs to serve 1 million requests per second, which means you can't do 1 million joins on 50 different tables. And so in our case, what we do is we write one kind of model to a message log. Then we have some kind of process which takes all of these model updates. It transforms them and creates a new read-oriented model and stores that in a different database. That's actually a key value store, read-oriented low latency key value store. And that's the right path of the CQRS, right? And so usually in CQRS, what you will have is an asynchronous write path where you queue up a bunch of updates, you run some sort of domain logic on them and create your write model from those. There'll be some kind of change notification, which will create the read model. And the read model is queried synchronously because oftentimes in almost all UI applications and a lot of other types of applications, the read path in the system, it makes a lot more sense to make it synchronous. It's actually very hard to imagine, for example, an application or a website where the read is asynchronous, where you queue up the read and then your client waits for it and gets the data and then presents it or something like that. It just makes so much sense. It's easier to debug to just have a synchronous request to the read path. But the write path, it's obviously much more scalable and much more robust if you make it asynchronous, right? And so for CQRS, if you look at all the patterns we talked about, it makes perfect sense to have some kind of message log as your command queue. You have some kind of consumer which will take it and create a new queue of write data models, some kind of persistence layer which takes updates from the write model again as a queue into the read model, and only then there's some kind of service which serves it. So our version 1 of our system was almost entirely synchronous, and one of the biggest problems that we had was the two conflicting load types on our user identity system, where we had spikes of writes whenever we updated the database and a consistent stream of reads from the same database. And every now and then, because the reads are constant, but writes are spiky, it will just overload the system and fail most of the reads. And then the website will become unstable. And one of the first things we did was actually separate the component that reads data from the component that writes data to make sure they're actually independent from each other. That's a big part of why you would actually consider using CQRS in your system. That brings us to event sourcing because they're often used together. Event sourcing is not necessary for CQRS, but very often you will actually use them together. What event sourcing does is it's a pattern where instead of storing the latest snapshot of data, you store all the possible updates of that data, right? And so, for example, if you in our case, the system I talked about earlier, which calculates the user type according to their title, we do store all of the title updates for every user forever, so that we can run over them and reconstruct the system if it ever goes down or if we need to recalculate with a new algorithm. So if you imagine there's let's say an infinite table of key value pairs, where the key in this case is A and B, and the value is some change you need to make on the object. Your materialized table, right, your, let's say a SQL database, would be just the final version of it, which is applying whatever operation you had on all the queue. But your event store would have all the possible events. A classic example of this, which is almost never used, but is always talked about in blogs and talks, is a shopping cart. Let's say you go to your eBay or Amazon shopping cart, you put something in a shopping cart, you put another thing in a shopping cart, then you delete something because you don't want to pay it. And eventually, what you pay for is just a snapshot, your latest version of the shopping cart. But the vendor actually cares very much about all the changes which happen to the shopping cart, because they might, if you put something in there and you take it out, they might want to try and sell it to you later and send you some ads, because everybody loves ads and vendors love sending ads. And so that's a perfect example of event sourcing, right? So if you take all of those together, we get basically full coverage of all the various patterns that are very commonly used in asynchronous systems. Most of them don't really have a synchronous analog, right? Except for request response, which is obviously very straightforward. That's not because, again, there's necessarily something better or worse about synchronous patterns. It's just synchronous patterns are much more straightforward. And so there's fewer patterns you need to cover. Now that you have patterns, we need to talk about delivery guarantees, which is something we ignored for most of this talk. We assumed that the message transport is magical. But the thing is, it's not magical. Message transports fail quite a bit. And so understanding what delivery guarantees you get from your message transport is important in order to implement every possible pattern. Because how can you, for example, implement event sourcing if you're not guaranteed that every message will reach the destination? If your event sourcing relies on applying every operation and you miss 2 of the messages, the result is going to be incorrect. And so broadly speaking, there are 3 delivery guarantees we can talk about in the messaging system. At most once, which means every message will be delivered to the subscriber, consumer, whatever you're going to call it, at most once, which means it might be 0 times or it might be 1 time. let's think about the kind of application. Again, we can go back to the stock ticker. A stock ticker is a classical example of it most ones. It's a lossy system. It's guaranteed that you will get each stock tick at most once, but you might skip some of them. There are some practical uses for that kind of system. Again, mainly statistics-based applications or things that just need to show a snapshot, UI-based applications. What we're doing right now, video streaming. If you think about, you're seeing me. If your network skips a few network packets of the video or the audio, it's no big deal. It's not going to be noticeable. So video and messaging delivery patterns are at most once. The most basic internet protocol, which is UDP, is of course at most once lossy pattern, right? The up to that is at least once. You're guaranteed that every message gets delivered at least once, which means it can be delivered more than once. This is by far the most common pattern in message queues. We'll get to exactly once in a bit. It's kind of a bit of a unicorn, but in practical terms, most message queues designed today have at least once delivery, which means you're guaranteed to get every message. You're not going to lose any data, but it's very likely that you'll get some messages more than once. Depending on how you set up the system and stability and various other considerations, you might get a lot of messages more than once. This has two implications. One, if we're building asynchronous systems with at least once guarantees, we have to consider idempotency. Every service has to assume it will get the message more than once. And if we have side effects from the service, side effects being you write to a database, you send an email notification, you do anything with the message, you need to consider how to make it as idempotent as possible. It's not always possible. As an example, we have an alerting system in our product, which if some user performs malicious activity, it sends an email to the administrator. An email is not idempotent, right? You can't take it back. You can't. If you send it again, you'll send another email. There's no way to override an email because you sent it and it's a side effect that happens and it went away. But for most other things like writing to a database, we do our very best to model data in a way that if you apply the same update more than once, it will not change the final result. This has very important implication on things like counting on stream or stream statistics. Right, one of the most, let's say, least understood and things where, let me put it this way: have you ever had a product manager or someone come to you and say, "Oh, let's do this. It sounds easy. I would just count all the items in the stream." I had this happen a year ago where someone wanted to know how many activities we had in a day in our system, how many activities in the stream. It's roughly about 1 billion per day. And so we went and said, okay, we'll need to build a system which can do BI analytics on 1 billion items per day, which means we have 300 billions of those per year. It's going to take a couple of weeks to build something like that. And said, no, but why don't you just count every message? You see every message, just count them. But that's not the way it works. You might skip some messages. You might send some messages more than once. Counting a live stream is an extremely complex engineering problem. Almost certainly you will overcount. Depending on how you store the counter in memory or in a state, you might undercount. It's almost impossible for you to count exactly. There are actually, and we're not going to have this in time for this in talk, but there are a lot of probabilistic algorithms which can very efficiently do things like counting and statistics on a stream of data and give you an approximation in a constant amount of memory. So look for probabilistic data structure. It's a fascinating topic, but it's the topic for next year's talk. So as I said, at least once delivery. If you, for example, try to count messages in the stream, it's very likely that some messages will be repeated, so you'll overcount. Within at most one system, you'll probably undercount. Examples of why at least one systems exist. Let's think about things like Kafka or Kinesis or pretty much any message queue. The way it works is when you consume a message, the consumer gets a message or a batch of messages, does something with them, and then it needs to send an acknowledgement to the transport saying, I finished with the messages. If the consumer process crashes before it sends the acknowledgement, the next time it goes up, it will get the same messages because they weren't acknowledged. And depending on the different flavors of transport, it might be one message, it might be a batch of 1,000 messages or a bulk of whatever it is, right? Again, Kafka, because I'm most familiar with Kafka, has two different modes. The standard Kafka consumer reads a batch of messages up to a certain size, and you acknowledge the entire batch all at once, commit the offset for the batch all at once, which means if you fail to commit the offset but you still processed most of the batch. Next time you will repeat all of those messages again. With Kafka streams, there is a single message acknowledgement, so you acknowledge every individual message. So you will repeat at most one message, but you will still repeat that one. Right. And so the golden unicorn is, of course, why can't we have exactly once delivery? And the answer is we can in very specific, very narrow circumstances. And the circumstances are if you don't have any side effects, and if you are reading and writing messages from the same message transport, and the message transport supports transactions, then you might have exactly once message delivery. So to narrow it down to a practical scope, if your system reads from one Kafka topic, writes to a different Kafka topic on the same Kafka cluster, and all it does is change the message. It doesn't do side effects. It doesn't call any other external systems or databases. Then what it can do is it can commit the offset for the consumption and the production at the same time. And then if the process crashes, then the outgoing message also won't be committed, and the incoming message won't be committed. And so in those narrow circumstances, you can have exactly once message delivery. If you change any of those variables, it will no longer be exactly once. Because, for example, if you call to external database to enrich your data along the way, if your process crashes, it comes back, it will get the same message, but the external system you call to might have changed in the meantime. So it won't be idempotent. If you need to read the message from one transport and write the outgoing message to a different transport, there's no way to make a transaction between those two. You have to commit the message first, then you can crash before you committed the output message, and so you have to break, which means you have to change the order around. You will commit the outgoing message first, then you will commit the consumed message offset, but then if you crash between any one of those two lines, you will get the message again. So basically, pretty much changing any parameter in that specific scenario bring us either to at most once delivery or at least once delivery, right? And so I don't think it's a practical goal to chase. I don't think it's important. I think most systems can be practically made to work well enough with at least once delivery, and in some cases, at most once actually makes sense. So that, of course, brings us to transactions, right? Because I mentioned transactions just earlier. We won't have kind of time. Again, it's a whole talk in itself. There's a lot of literature about distributed transactions, but I'll run through this real quick, just so you have a sense of how complex of a beast we're chasing here. So unlike standard synchronous single node systems where transactions are easy, so to speak, because your database or wherever else gives you transactions for free, distributed systems are very complex and transactions just don't work very well across processes. So there are a few ways to provide some form of transactionality in a distributed asynchronous systems. The first one is a two-phase commit. Two-phase commit is a distributed protocol that is synchronous. It relies on being synchronous. And I'm not going to go into the details of the algorithm, but basically it breaks a large atomic transaction into a series of steps where every step is unique. And you can, if the transaction fails in the middle, you can recreate and either continue from the previous step or roll it back. It's very complex. It's usually impractical to implement for performance reasons because it takes a lot of operations. We won't go into it. But for our purposes, for asynchronous systems, there are a couple of very useful transactions. One is called the Saga and the Transactional Outbox, and those go together. So Transactional Outbox is a very common use case in asynchronous systems. Imagine you have a service which gets a message, does something with it, puts the result in a database, and then sends an outgoing message. And what you want to do is you only want to send the outgoing message if you succeeded in updating the database. For example, something that we have a lot of in our system, updating a cache. We get a message, we want to process the message, we want to update an in-memory cache, which is a separate process, and then we want to post the result to a permanent store as well. For example, in our case, to S3. Right, and so we want to update the database and send an outgoing message as a transaction. If we fail to update the cache, we don't want to send the message. If we fail to send the message, we don't want to update the cache because that would cause an inconsistency in the system. And so this only works, again, in a specific case where you can split the operation of updating the database and sending a message into two steps. Imagine you have a database with two tables. One table is the entity table. The other table is, let's call it an outbox, like a message outbox table. If you can transactionally update both tables, you update the actual entity table, and then you update the outgoing messages table, which says post this message to the outgoing queue. That can happen as a transaction, and that can be guaranteed to either happen together or not at all. And then on the outgoing table, you would have some kind of separate process reading the outbox table, picking up the outbox messages, and publishing them to the outgoing queue. Now, in this case, you are guaranteed, in fact, to either post and update at the same time or fail to do both at the same time, but you won't have an inconsistent system. Is this practical? And it's a question I get a lot. No, it's not really practical. We don't do this. We have this use case a lot in the system, and we specifically avoid using transactional outboxes because it limits you to using the kind of data stores which support transactions. In our case, our scale is in the billions. There is no system which can do transactions and is fast enough to actually serve as a cache or some kind of backend for us. So in our case, we just post the message first, then we update the cache, and we live with the consequences of having a stale cache. And hopefully it will eventually get consistent. It's just a trade-off we make. We understand the limitation of the system, and we make it, it's not a surprise to us. We could do the reverse trace. We could trade-off. We could update the cache first and then post the message, and that would have a different set of failure modes. And again, that's a trade-off we would make reasonably, right? But the one pattern that we actually do have quite a lot is the Saga pattern. And so this is actually a very common case. Let's say you have a process in your system which has multiple steps, and you want all of those steps to eventually happen, or if some of them fail, you want to actually cancel all the ones you've succeeded. This is extremely common. Again, in our system, an event comes in, and we have to update a bunch of data stores and spawn off a bunch of sub-processes which go and create alerts, send notifications, do a bunch of stuff. And we want all of those actually to succeed eventually. We don't actually, it doesn't have to happen immediately, but eventually they all have to succeed. Or if some of them time out, we stop waiting for them, we want to roll back all the other things we did. Right? And so this is called a Saga, which means because it doesn't happen in a single database or even in a single system, we have to take this logical transaction and break it up into a bunch of steps. And each service will serve a step. And then we have to persist the context of where we are in this logical transaction together with the object that we're moving from service to service. So let's take as an example, your standard order service, right? An order comes in from the website, we have your order object, and when the order happens, we want to pay some money, we want to update the inventory, and we want to, call the shipping service and schedule a delivery. Now, each one of those is actually independent, but we do want to have all of them happen or none of them to happen, right? Because we don't want to send a delivery if we didn't charge the payment service. And so there are two ways to do this. One is called coordination, where there's one service which is chosen as the coordinator, and that service has all the domain logic of how the transaction needs to happen. It will send one message to the order service, it will send one message to the payment service, and it will send one message to the shipment service, and it will expect a response back. So in this case, we're using a request response pattern. It will send separate messages to every subsystem. It will get the results from all of them, combine them all together, and then our Saga will be complete. And at every point, we have a record of where we are in the transaction. If the coordinator decides that too much time has passed and we need to roll back the Saga, it will send the reverse message to the service. For example, if we already scheduled the delivery, it will send a cancel delivery message to the delivery service. But if we didn't do the payment, it won't have to cancel the payment. The other way to do this is called choreography, which is you don't have a central coordinator system which does all of this. You overload all of the context information on the message itself. And so in our case, we would send a message to the, let's say, the payment system and say, this is a order, do the payment bit. The payment system will do the payment stuff, attach the acknowledgement that the payment was proceeded to the message, and send it on to the next service in the transaction. And for example, the inventory. The inventory service would update the inventory, overload the success message on the same message to add to the context, send it on to the shipment service. That would create a shipment. And when the shipment succeeded, the shipment service will, again, update the giant Saga transaction we have and, send it to the completion or fulfillment service. Right? And so at any point, if one of those fails, it can send the transaction in the other direction in what's called a complementary transactions. So we'll talk about this. A successful Saga would be, we'll start T1, point transaction 1, and then end it, start the next step, start and end the next step, and then the final service in the chain ends the Saga. The downside of this is that every service is tightly coupled to your domain logic, right? Every service needs to know what happens after it and what happens before it. If you want to rewire the order, because now there's a fourth service in the middle, you have to change 3 components. You have to change the fourth service you're adding and the 2 services on either side of that, because now they need to be aware of what happens before them, what happens after them. With the orchestrator, the opposite is true, right? You don't have any domain logic in each, or any routing logic in every service, but now you have a single point of failure, which kind of isn't what we're going for in a distributed system. You have one service which has to handle everything. It has to have all the acknowledgements, and it probably has to have state, because you can't store all of this transaction information in memory. It forces the orchestrator service to have a database in some kind of state, and that has scaling and performance implications. And so that's a trade-off you have to make for yourself. For most of our systems, we go with choreography, which means every service knows what needs to happen after it, if it's part of a transaction, mainly because we really want to avoid bottlenecks on the sort of orchestrating service, right? And so if the transaction fails in the middle, what happens is the service where it fails has to go and create what's called a complementary transaction. So if we charge the person, we need to create a message which reverses the charge and send that in the other direction of the transaction. And if there's another operation that needs to be canceled, then the payment service needs to know that part of the canceling transaction is to send a new message to the service that came before it, which is part of the reason why it's actually complicated to do that. So towards the end of the talk, I'm actually going to skip over the technologies. This is something you can Google online. There's a million different message queues, and they all have their pluses and minuses. But what I really want to talk about is backpressure. Backpressure is a very important consideration for us. It's any system which has any kind of scale will have this question of what happens if a consumer service cannot keep up with the producer service, right? And so you have 2 ways of handling backpressure, which means the consumer service will need to tell the producer to produce less. In a synchronous system, there's no backpressure, it's inherent, right? Because the second service fails and then the first service knows it got overloaded. But in an asynchronous system, service B can fail and the messages will continue queuing up in the transport infinitely, right? And so we have 2 ways. One is we can have some kind of flow control, which means service B, the receiving service, would have a way to tell the sending service to slow down. The main problem with that is it brings us right back into synchronous territory, because that means that service A becomes unavailable at the same time or slightly after service B becomes unavailable. Our other choice, of course, is to not throttle or not do any kind of backpressure, which means the queue or the message transport in between the 2 services will continue growing until we either fix the problem with B, and in this case, we have to usually scale out B a lot more to handle all the backlog of messages, or the message transport fails. There's no right answer to this. You have to figure out what it is that you need. Obviously, the right answer is don't have scaling problems, scale out automatically, but that's not always possible. For most cases, again, this is a trade-off we make in our system, and it will be a different set of considerations for every other system. We almost always choose the option on the right, which is we choose to grow the queue infinitely, and we allocate all of our message transports with huge buffers of free disk space to queue up indefinitely, because we prefer to potentially reprocess 2 days worth of messages back than to lose data. But again, that's because losing data is the worst of the 2 trade-offs in our system for the kind of product we have, and for different products, that's going to be a different trade-off, right? But of course, basically, it's like we talked at the start of the talk, because it's an asynchronous system, we convert any kind of failures into lag, into latency. And when we have lag, we have to eventually consume all of this lag, which means scaling out whatever it's consuming. And again, last thing before we finish the talk, error handling. Again, because unlike synchronous systems where error handling is very straightforward, you get the exception to the requester or all the way up the chain, and you can handle it there because it's coupled in time. With an asynchronous system, the error might happen an hour from now. It might happen on a specific component. So what do? Let's imagine we have a queue of messages. We have to process all of them. And process B is doing the consuming. It will process message 1, message 2, and it will then fail to process message 3. What does it do? There are 3 broad categories of error handling in asynchronous message systems. One is they can continue retrying message 3 forever. Eventually, it might happen if it's a transient error, if it's a timeout or a database problem, we can keep retrying until it actually succeeds. This makes sense if you can confidently identify that the error is transient. It's caused by something that's not, the problem is with the message itself, the problem is with an external component, and it will eventually go away. And so retrying in place is a strategy where it makes sense if you know the error is transient. If you don't want to block the queue, if you think the retrying is going to take too long, you can do what's called retry out of order. It means that you give up order of delivery, you take the message out of the queue, you put it in a different queue or some other place, and then you have some kind of scheduler to try that message again. And maybe then you will succeed. But in this case, you can continue processing the rest of the queue and not cause a traffic jam, so to speak, right? You will want to lose throughput. The last option, of course, is a dead letter queue. If you can't do anything with the message, the problem is the message itself. There's no point retrying it. There's really nothing else you can do. You have to take it out of the queue. You have to put it somewhere else, usually called a DLQ, a dead letter queue. And then in most systems, it's something that you manually look at. There's no automatic system to handle DLQ because that's the final resting place of messages you couldn't deliver. This is it. We're done exactly on time, 1 minute over. Thank you very much for your attention. I'm very happy to answer some questions. I don't see anyone writing in chat in WebEx, but let's see, maybe someone wrote something in Slack. Nobody wrote anything in Slack. You people are very, either know more than me about this topic, so you have nothing to answer to question about, or you're very shy. I'm not sure, whichever that is. But whatever the case may be, I'm going to hang out in Slack for a bit more. And so I'm happy to answer questions if you have any, or you can see me typing in Slack and you can reach out to me separately. Otherwise, thank you very much for coming to the talk. Hope you learned something interesting today. Have an excellent rest of the conference.